All right. In this final lecture in this series, we will be discussing compound Poisson processes. Let's just start with a definition. A compound Poisson process is a real valued right continuous process, which we'll call Z, mapping from our sample space omega to the non-negative real numbers R plus, indexed by R plus, usually representing time. It has the following key properties. First, finitely many jumps for any outcome omega in omega, the sample path t maps to zt of omega, and this path has only a finite number of jumps within any finite time interval. Second, independent increments. For all non-negative t and s, the increment zt plus s minus zt is independent of the past history of the process up to time t. We denote this history as script f sub t, which is the sigma algebra generated by zu for all u less than or equal to t. And third, stationary increments. For all non-negative t and s, the distribution of the increment z t plus s minus zt depends only on the length of the interval s and not on the starting time t. For each outcome omega in omega and each natural number n, we can define the time and the size of the nth jump. The jump times are s tilde sub 0 of omega, which is 0, and s tilde sub n of omega, which is the infimum of all times t greater than s tilde sub n minus 1, such that zt of omega is not equal to z at time s tilde sub n minus 1 of omega. The jump sizes are y naught of omega, which is 0, and yn of omega, which is z at time s tilde sub n of omega minus z at time s tilde sub n minus 1 of omega. A quick reminder, recall that script f sub s, defined as the sigma algebra of zu for u in the half open interval 0, s represents the collection of historical events associated with the process z up to time s. If s tilde sub n is almost surely finite for all n in the natural numbers, then the sequence of jump times s tilde mapping from omega to r plus raised to n forms a sequence of stopping times with respect to the natural filtration script f bullet of the process z. Another reminder, let n mapping from omega to z plus raised to r plus be the simple counting process associated with the number of jumps of our compound Poisson process z in the half open interval 0.t. This is defined as nt equals the sum over n in natural numbers of the indicator that s tilde sub n is less than or equal to t for all t in r plus. Then s tilde sub n and yn are respectively the arrival instant or jump instant and the size of the nth jump. With these definitions, we can express the compound Poisson process zt as the sum from I equals 1 to nt of yi. Now for a key proposition, a stochastic process z mapping from omega to r plus raised to r plus is a compound Poisson process if and only if its jump times form a Poisson process and the jump sizes form an independent and identically distributed IID random sequence that is also independent of these jump times. Let's sketch the proof, which we'll do in 2 steps. First, the implication, let z be a compound Poisson process with the jump instant sequence s tilde and the jump size sequence y. We need to show that the associated counting process n is simple and has stationary and independent increments and that the jump size sequence y is IID. Continuing with the implication part of the proof regarding the independence of jumps and increments, from the definition of the jump instant sequence S tilde, it follows that the counting process N is adapted to the natural filtration script F bullet of the compound Poisson process Z. Since the increment Zt plus S minus Zt can be written as the sum from I equals Nt plus 1 to Nt plus S of Yi, and because compound Poisson processes inherently have independent increments, it follows that the increment in the counts Nt plus S minus Nt for S greater than or equal to 0 and the sequence of future jump sizes Ynt plus J for J in natural numbers are both independent of the past history script F sub T. Now for stationarity, let's assume for simplicity that all jump sizes are positive. Then S tilde sub n is the infimum of t greater than S tilde sub n minus 1, such that Zt is greater than Z at S tilde sub n minus 1. Also, the event that Nt plus S minus Nt equals 0 is equivalent to the event that Zt plus S minus Zt equals 0. From the stationarity of the increments of Z, it follows that the probability that Nt plus S minus Nt equals 0 is independent of T. This probability must be of the form e to the power minus lambda S for some non-negative lambda. It then follows that the counting process N has stationary increments and the associated jump sequence S tilde forms a homogeneous Poisson process with intensity density lambda. Continuing with the implication part of the proof regarding strong Markovity, the compound Poisson process possesses the Markov property which stems from its stationary and independent increment property. Furthermore, since each sample path T maps to Z T and is right continuous, the process also satisfies the strong Markov property at each almost sure stopping time. Now for the interjump times being IID, we will show inductively that S tilde is a sequence of stopping times. Consequently, the sequence of interjump times x, where xn is S tilde sub n minus S tilde sub n minus 1, is an IID sequence. We've already established that S tilde 1, the first jump time follows an exponential distribution, so it's almost surely finite and thus a stopping time. From the stationarity of increments of the compound Poisson process and the strong Markov property at the stopping time S tilde 1, it follows that S tilde 2 minus S tilde 1 is independent of the history up to S tilde 1 script F sub S tilde 1 and is identically distributed to S tilde 1. The result for all interjump times then follows by induction. Continuing the implication part of the proof, for the jump sizes being IID by the strong Markov property of Z, the nth jump size Yn is independent of the past history script F sub S tilde n minus 1, which is the sigma algebra of ZU for U up to S tilde sub n minus 1. Furthermore, due to stationarity, Yn is identically distributed to Y1 for every n. It follows that the jump size sequence Y is IID and also independent of the jump instant sequence S tilde. Regarding superposition, similar arguments can be used if we allow for negative jump sizes. For real valued jump sizes, both positive and negative, we can conceptualize this by forming two independent Poisson processes. one for positive jumps and one for negative jumps. The superposition of these two processes would then also be a Poisson process or related to it, leading to a Levy process. Now for the converse part of the proof, let X be an IID interjump sequence where each Xi is exponentially distributed with rate lambda. Let Y be an IID jump size sequence independent of X, where Yi can be real valued. We can then define the jump instant sequence S tilde, where S tilde sub n is the sum from I equals 1 to n of Xi. The counting process for the number of jumps n is defined as nt equals the sum over n in natural numbers of the indicator that S tilde sub n is less than or equal to t. And finally, the compound process z is defined as zt equals the sum from n equals 1 to nt of yn. First, finitely many jumps. Since nt, the number of jumps from a Poisson process by time t, is finite for any finite t, it follows that the compound process z constructed this way will also have finitely many jumps in any finite interval. Continuing the converse part of the proof, regarding independence of increments for any finite n and any collection of disjoint finite intervals, I from 1 to n, we can write z of I, the total jump in interval I, as the sum from k equals 1 to n of I of yik, where yik denotes the kth jump size that occurs within the interval I. Since the sequence of counts n of I for I from 1 to n are independent because they correspond to counts of a Poisson process in disjoint intervals, and the jump size sequence y is also IID and mutually independent of the n of i's, it follows that the z of I values are independent. Regarding stationarity of increments, further, the stationarity of the increments of this constructed compound process z can be inferred by looking at the distribution of z of I. The probability that z of I is less than or equal to x can be found by summing over all possible numbers of jumps m in that interval. The sum over m in z plus of the probability that z of I is less than or equal to x and n of I equals m. This is the sum over m in z plus of the probability that the sum from k equals 1 to m of yik is less than or equal to x times the probability that n of I equals m. Since n of I is Poisson with the rate proportional to the length of I and y are IID, this distribution will only depend on the length of I, not its starting point, establishing stationarity. Let's look at some examples of compound Poisson processes. First example, imagine customers arriving at a store. Their arrival follows a Poisson process and each customer, say customer I, spends an amount xi, and these amounts are IID and independent of the arrival process. We can define y not as 0 and yn as the sum from I equals 1 to n of xi. Now if we define zt as ynt, this zt represents the total amount spent by all customers who have arrived up to time t. This z is a compound Poisson process. Second example, consider a machine that is subject to failures. Let the time between successive failures be independent and exponentially distributed, meaning failures occur according to a Poisson process. Each time a failure occurs, there is a cost of repair, and these repair costs are random variables at each failure. Then the total cost of repair accumulated up to a certain time t is also a compound Poisson process. This concludes our lecture on compound Poisson processes.